Hello, welcome to this new lecture of the course Transportation Network Analysis. So, in the last lecture, we had started to see some important properties of unconstrained optimization problems, and today we will be looking at constrained optimization problems. So, note that in constrained optimization, it is possible to have an optimum where the gradient does not vanish. So, without loss of generality, suppose the optimization problem is a minimization problem. Okay. So, we can have a minimum where the gradient does not vanish. So, this is different from the case of the unconstrained optimization, where the necessary condition for a minimum to exist at a point x star is that the derivative at that point should be equal to 0. Okay, so, this we had seen in the last lecture, but this need not hold true when we have constrained optimization. So, let us look through this an example. Suppose we are minimizing this function zx here as shown on the right here, and we have this constraint that x is greater than or equal to a and x is less than or equal to b. Okay. So, that means that the feasible region is restricted in this area, okay, in this line segment here a to b. So, now you can see that the minimum value of z occurs at point b, okay, but here the slope of the function is not equal to 0. Okay. So, therefore, the concepts that we had learned in the unconstrained optimization case need not hold always true for the constrained optimization case. So, this is saying the same things, that we have these two constraints here in this example, x greater than or equal to 1 and x less than or equal to b. So, the minimum lies at b, but the derivative of the function is not 0 at b. Okay. So, this is the important motivation for focusing on constrained optimization in a slightly non-trivial way as compared to what we are doing in the unconstrained optimization case. Okay. So, we need to modify the conditions for finding the minimum in the constrained optimization. So, whatever we had learned in the unconstrained optimization, that will not necessarily hold true. So, before we look at the important concepts here, we will be mentioning that we only focus on problems that possess a finite minimum which occurs at a finite value of x. Okay. Now, to ensure that we are always focusing on such kind of problems where the minimum value is finite and it occurs at a finite value of x, some regularity conditions will be assumed. What are those? First is that the objective function has to be continuous over the feasible region, okay, and the feasible region has to be closed and bounded. Now, I hope everyone knows what a continuous function means. Okay. So, if you do not know that, I will suggest that you quickly check the standard mathematics book in the undergraduate level. So, in a very layman language, a function is said to be continuous if you can, for example, draw it without lifting the pen. Okay. So, an uncontinuous or discontinuous function example is like this. Suppose you have a function here and this is the x direction. So, suppose you have a function like this here. Okay. So, here there is a discontinuity at this point. Okay. So, this is an example of a discontinuous function. So, we will be only focusing on those optimization problems where the objective function is continuous over the feasible region and the feasible region has to be closed and bounded. Now, we all understand what bounded feasible region mean. For example, an example of a unbounded feasible region is like this, that suppose you have two dimensions here, x1 and x2, and suppose the feasible region is consisting of this first quadrant here. Okay. So, this whole first quadrant is not bounded because there is no limit to what these values x1 and x2 can take, because they can go as high as to infinity. Okay. And the other thing is that this feasible region has to be closed. What does closed mean? That an example of closed feasible region is that suppose we have a single dimension case, that is suppose a function is only varying with x. So, then an interval like this a comma b, where these are square brackets, if this is a feasible region of that problem, so then this is a closed feasible region. An example of an open feasible region will be something like this, okay, where we have these kind of parentheses. Okay. So, for example, this is a closed feasible region where both the endpoints 0 and 1 lie in this feasible region, whereas this is an example of a open feasible region because the endpoints here 0 and 1 do not lie in this feasible region. And also we assume that the objective function and constraints are all continuously differentiable. What does that mean? So, note that there is a difference between a function being differentiable and being continuously differentiable. Now, a function is said to be differentiable if its derivative exists at every point, okay, whereas it is said to be continuously differentiable if its derivative function is continuous function, okay. So, that is the difference here. Okay, so we will be assuming that whatever objective functions and the constraints that we will be focusing on, they will be satisfying these conditions here. And since these conditions will be satisfied, it will be guaranteed that this problem will possess finite minimum and it will occur at a finite value of x. Okay. Now, you do not need to remember always what are these conditions, for example, but this is just mentioned for completeness sake so that you know that whatever concepts will be shown in the subsequent slides, there is some underlying assumption on the objective function and the constraints for which they are valid. Okay. Okay, so let us now start developing the first order conditions for constraint optimization problems. And again, as we had done in the unconstrained optimization case, we were first focusing on the single dimension case where the function was only varying with one variable, and then we had extended the same concepts for the multivariate cases. So, here also in the constraint optimization case we will be focusing on single dimension so that we can get some intuition, and then it will be easier to extend those concepts when we have multiple dimensions or multiple variables. Okay. Okay. So, we are first focusing on developing first order conditions. So, if it was unconstrained optimization case and it was single dimension, so the first order condition is that the slope of the function at the minimum should be equal to 0. Okay. So, that is the first order necessary condition, but as we had seen in the starting of this lecture that it may not necessarily be the case in the constraint optimization case. Okay. So, suppose we have this function zx here, okay, and suppose this is defined over this feasible region a dash to a double dash. Okay. So, this is the diagram that we are focusing on. So, on the y axis we have zx here, and then on the horizontal axis we have x, and here we have these two values a dash and a double dash. Okay. Now, just to again emphasize one more point, all of this discussion that we have been doing since the starting of the traffic assignment and then we digress towards this continuous optimization theory, all of this is available in this book by Yosef Sheffi on urban transportation networks. So, that is kind of a reference that you can always check, okay, in addition to these slides, although these slides are complete in a particular way, but there can be some more examples and so on which you can find in that book also. Okay. So, here in this figure that is shown, the minimum point for this function zx is inside the feasible region because the minimum is occurring here, okay, and this is between these two endpoints a dash and a double dash, and at this minimum the derivative is equal to 0, okay. So, this holds, okay, but this may not always be the case. So, let us consider another scenario here. Again we are minimizing this function zx, but the minimum point now occurs at this x equal to a dash. So, let us represent this optimal solution by x star here. So, now x star is equal to a dash. Now, you can see that the derivative of the function at this x equal to a dash is not equal to 0. So, here the derivative is not 0, it is something positive, okay. So, when the minimum of the function is on the boundary of the feasible region, the following observations can be made. So, this is one of the boundaries of the feasible region. This is one boundary a dash and this is the other boundary a double dash, okay. So, this is the observation here that if the constraint on which the solution lies, now that constraint on which the optimal solution lies is called the binding constraint, okay. So, if this kind of constraint is of the form x greater than equal to some constant, then zx must be increasing, or to be very precise, non-decreasing at x star. So, let us look at this diagram here. So, this constraint here is in fact of this form x greater than equal to a dash, okay. So, this we had mentioned. So, it satisfies this condition, and this is the binding constraint because the optimal solution is here, because the zx takes the minimum value at this point. So, this is saying then if that is the case, then zx must be increasing, or to be very precisely non decreasing at x star. So, you can see here that the slope of the function at this point is in fact positive here. Okay. So, this satisfies this condition here, that zx must be increasing, or to be very precise, non decreasing at x star. Okay. Now, another situation that can arise is that now suppose the optimal solution x star is at a double dash, that is on the other boundary that we have for the feasible region. Now, this falls in this case, that if the binding constraint is of the form x less than or equal to something, then zx must be decreasing, or to be very precise, non increasing at x star. Okay. So, this constraint is of this form, that x has to be less than or equal to a double dash, and we can convert it. So, this is equivalent to saying that minus x is greater than or equal to minus a double dash. Okay. So, remember that. Now, this constraint is of this form, that x is less than or equal to some constant. So, here you can see that at this point where the minimum exists, the slope of the function is decreasing in fact, okay, which satisfies this condition. Okay. So, therefore, this problem can be written in the following form. So, this is the optimization problem that we are focusing on. Minimize the function zx. We have two constraints, x greater than or equal to a dash, and this is the equivalent way of saying that x has to be less than or equal to a double dash. Okay. So, we have converted this constraint also in this form, so that both of the constraints are something like a function g is greater than or equal to some constant b, and we will get to know in the next few slides why this is useful. So, here as I said, we have expressed this in the standard form here, this optimization problem, that we have these constraints like g1x greater than or equal to b1, then we have the next constraint g2x greater than or equal to b2. Now, here g1x is same as x, b1 is same as a dash. So, this gives us this constraint here, g2x is the same as minus x, and b2 is same as minus a double dash. Okay. Okay. So, when the constraints are expressed in the standard form that we just saw, we can say that the derivative of the function z at x star and the derivative of the binding constraint at this point, which is given by g by dx at x star, will always have the same sign. Okay. Now, let us see why is that the case here. So, we can see here in this left case, the binding constraint is this one, that x is greater than or equal to a dash, okay, because the minimum lies here. Okay. So, this constraint when we are expressing in the standard form, so here g1x is equal to x here. Okay. So, this derivative of g1x with respect to x is what? It is equal to 1, okay, and the slope of the function at this point is positive. Okay. So, the sign of this thing 1 and the sign of this both are having the same signs, because both of them are positive. Similarly, if we look at this right figure here, then the binding constraint in this case is what? Minus x greater than or equal to minus a double dash. Okay. So, here g2x is equal to minus x. So, the derivative of g2x with respect to minus x is what? It is equal to minus 1, okay, which is mentioned here, and the slope of the function here at this optimal point is also negative. So, this is also negative, and same is this derivative of z with respect to x. So, both of them have the same signs. So, that is what is being said in this point here. Okay. So, this is the important concept here, that since both the derivatives are scalars, the condition of same signs can be written as this here, that derivative of function z with respect to x at x star is equal to uj times the derivative of gj by x at x star, either when j is equal to 1 or j is equal to 2, and it is given that uj is a non-negative scalar and gjx is the binding constraint. Just take a look at this and try to see that this is exactly what we had seen in the last slide. Okay. So, we had two cases, right? In the first case, the binding constraint was x greater than or equal to a dash. Okay. So, in that case, this derivative of g1 with respect to x at this point x star equal to a dash was equal to what? This is equal to 1 because g1x is equal to x, okay, and the slope of the function dz by dx was positive, okay. So therefore in that case we can say that dz by dx is equal to some uj times dg1 by dx, okay. So in that case this holds for j equal to 1, okay, whereas in the other case when we had the optimal solution at minus a double dash, then the binding constraint was this minus x greater than equal to minus a double dash, okay. So there the derivative of g2 with respect to x is equal to minus 1 and the slope of the function at a double dash was negative, okay. So this can be expressed in this form, that derivative of the function at x star is some uj times some constant times the dg2 by dx, okay. So this is just the same way of saying that the sign of the binding constraint is the same as the slope of the function at that optimal point, okay. So this is that way of saying, and you can now understand that why it is either j equal to 1 or j equal to 2, because either one of these two constraints will be the binding one. Depending upon which one is the binding constraint, that is where the optimal solution lies, we will be having this condition, okay. Now note that in this case it is for either j equal to 1 or j equal to 2, okay. So both of these two will not hold together, but in order to develop a set of first order conditions that will apply in all the cases, that is we had seen three kind of cases. One is that the optimal solution is lying in the internal point, okay, it is neither at either of the two boundaries. So there we had seen the derivative of the function is equal to 0 at the optimal point, and then we had taken a look at these two cases. One of these cases the optimal solution was at x equal to a dash, and the other one it was at x equal to a double dash, okay. So in order to have a single condition that can represent all of these things, rather than we having these kind of expressions that OR thing holds, let us define non-negative variable uj for each of these constraints, okay, and this will not just be restricted to the binding ones here. So in this case here either j equal to 1 will hold or j equal to 2 will hold. So therefore u1, either u1 was defined or either u2 was defined, depending upon where the optimal solution lied at which one of the two boundary constraints, okay. So in this case both u1 and u2 cannot exist together here, but we now want to develop those conditions where both u1 and u2 can exist together, okay. But still uj, that is u1 and u2, they will still be non-negative variables. So let us look at those conditions where we can do away with this OR and both u1 and u2 will be defined together, okay. So if the jth constraint is not binding, that is gj x star is greater than bj, then let us define uj to be equal to 0, okay. Now you need to understand that why we are saying that gj x star is greater than bj when the constraint is not binding, because the way we have defined the constraint is like this: gj x is greater than equal to bj. I mean, this is the way we have defined the constraint, okay. So if this constraint is binding at x equal to x star, then what it means is that gj x star is equal to bj, and if it is not binding, then it means that gj x star is greater than bj. You can check this from the example that we had seen. So for example, when we had this case, the optimal solution was lying in the interior, so it was neither of the two, it was neither at the two boundaries, then the x star was greater than a and minus of x star was also greater than, this is a dash and this is minus of x star is also greater than minus of a double dash, okay, which is the same as saying that x star is less than a dash, okay. So x star greater than a dash and x star less than or equal to a double dash, that means that x star is lying in interior point of this feasible region from a dash to a double dash, okay. So in that case neither of these two constraints are binding, and then both u1 and u2 will be equal to 0. Okay, u1 is for the first binding constraint, this one, and u2 is for the second constraint here. Okay. So, in this case, when both of these constraints are not binding, that is the optimal solution is in the interior, then we will have u1 also equal to 0, u2 also equal to 0. And then we had considered the second case where actually x star was equal to a dash. Okay. So, in that case this was the binding constraint. Okay. So, in that case the non-binding constraint will be this, that we have this minus x star is greater than minus a double dash, which is the same as saying that x star is less than a double dash. Okay. Because if x star is equal to a dash, then x star has to be less than a double dash. So, in this case this is the non-binding constraint. So, then u2 will be equal to 0 in that case. Okay. And similarly, when we had the last case when x star was equal to a double dash. Okay. So, then this automatically means that x star is less than a dash, because the way we had defined was that a dash is less than a double dash. Okay. So, in that case this is the non-binding constraint, and therefore u1 will be equal to 0. Okay. Now, how to mathematically write this condition? So, this can be written in this form here. And why does this work? Because if a constraint is not binding, that is gj x star is greater than bj, so then this is not 0, but then if this condition has to hold, then uj will be forced to 0. Okay. So, that is why this condition is mathematically the same as this one. Okay. So, it means that either uj is equal to 0, in which case the jth constraint may or may not be binding, or uj is greater than 0 and the jth constraint is binding. Okay. Now, you might be thinking, why is this the same as this, the first one here? See, if the jth constraint is not binding, then uj is equal to 0. Okay. So, this is coming in this first part here, but if the jth constraint is binding, then that means that this will be equal to 0, bj minus gj x star. So, then whether uj is equal to 0 or it is greater than 0, both of the conditions are fine. Okay. So, that is why we have this thing written here. Okay. So, we will continue this in the next lecture also. Thank you.